So we've learned about privacy amplification, and we've seen how strong seeded extractors could be used in order to solve the task of privacy amplification. Now, the only thing that we have left to do is construct strong seeded extractors. And this is what we're going to see in this module and the coming ones. The way we'll do it is by establishing a connection between extractors and hash functions. So in order to explain the connection, let's look at extractors from a combinatorial point of view. To simplify things a little bit in this module, I'm going to ignore the side information E. So you can imagine that there's some E present there if you'd like, but it's simpler to put it aside for a little bit. So our task is to construct a function X that maps a string X with high enough min entropy into a string Z that looks like it's uniformly distributed. And so let's think of this combinatorially. So I can represent here in blue the whole universe on which X is distributed. So that's all possible n-bit strings. And on the right-hand side, I've put all possible m-bit strings. So that's the universe for Z. Now, what does it mean that X has min entropy at least k? As a first approximation, you can think of it as X being uniformly distributed on a subset of the whole universe. And what's the size of that subset? 2 to the k. So the larger the k, the more uncertainty we have, the larger the set in which X could be distributed. But it could be the set that I've drawn here, or it could be another set, for instance this set. This is unknown to us. And what we'd like is a procedure X, which is a map that sends any blue dot on the left to a blue dot on the right, such that whatever the distribution of X, as long as it's distributed over a big enough subset of the original set, then the output of the procedure is uniformly distributed in the range, so in the whole blue set. Now you can see once more why we're not going to be able to construct deterministic extractors, because whatever my extractor is, this input set is bigger than the output set, so I need to have a bunch of arrows that point to the same dot in the output. Let's say this one over there. So let's say maybe this point is also mapped here, and then this point is also mapped here, and then this point is also mapped here. And once I fix this function, so once all the arrows have been decided on, then I'll always be able to say, well, let me take my source X that is uniform on this set here, and then this is a set that would be completely mapped to the same point of my output, in which case the extractor would certainly not be secure, because for this source X, the output is completely determined. It's a single string. So that explains the role and the importance of the seed. You think of the seed as giving different possible maps. There's the map in black that is associated with one seed, the map in red that's associated with another seed, and maybe another map in blue. Instead of mapping this point to that point, it maps it to another one. This point, it maps it here. When we choose a random seed, we choose a random map, either the black or the blue or the red, and then the extractor is applied. Now the source has to be chosen before we choose which map is being applied, and that's what gives us some hope that constructing such extractors might be possible. So now let's try to do those based on hash functions, right? We're really trying to map a larger set containing the string X to a smaller set containing the string Z. So what are hash functions? Here's the first basic notion of a family of hash functions that we'll call a one-universal family of hash functions. So these hash functions are parameterized by an index y. Y ranges over the set of indices over which the family is defined. They map n bits to m bits. And the family is called universal if it is the case that for every z output and for every input x, the probability when I choose a random function from my family that it maps x to z is 2 to the minus m. So this guarantees that if I choose a random function, whatever the input, it's mapped to a uniformly random output. This looks like a desirable property. Let's find ways that we can achieve it. Here's an example. For instance, we could take y to be also an n-bit string, and then I could take fy of x to be simply the bit-by-bit parity of x and y. So I'll just take x plus y mod 2. Maybe I should write it as the XOR. So this is bit by bit XOR, right? And in this case, I'll also get an n-bit output. So this is one universal, because even if I fix x, then if I choose a random y, the value of the function on x will be uniformly distributed, because I take the parity with a uniformly random string. Is it secure? No. I claim that this doesn't give us a strong extractor. Why? Because if you're given y, you can recover x by taking, meaning that if this input x has not completely full min entropy, let's say one of the bits if x is fixed, the first bit, then when you're given the output z and the seed y, you want to distinguish this from a uniformly random string, you only have to take the parity, then you recover x and you look at the first bit and you see if it matches your side information or not. So this is not a strong seeded extractor. What we need, this condition, is a desirable condition, one universal, but in order to get a strong extractor, we're going to need something stronger. We're going to have to look at two universal families of hash function. So what's a two universal family of hash functions? It's something that satisfies the following condition. So it should be the case that for every z and z prime, and also for every x that is different from x prime, the probability not only that x is mapped to z, but also the probability that x prime is mapped to z prime, so that's why it's called two universal. I'm simultaneously looking at the value of the function on two different points. Then this probability should be the same as if we had chosen completely uniformly random strings, z and z prime, so it should be equal to 2 to the minus 2m. So that's the definition of a two universal family of hash functions. Let's see why the family that I introduced in the previous slide was not two universal. So example, if I take fy of x to be the parity of x and y, as before, this is not two universal. Why? Well, the probability that fy of x equals z, so that's the probability that x plus y equals z, and x prime plus y equals z prime, this is what? I can take the parity of the two equations, and it's going to be the same as the probability that x plus y equals z and x plus x prime equals z plus z prime. But now, z and z prime, this should hold for any z on z prime and any x different from x prime. But here you see that if the parity of z and z prime is not the same as the parity of x prime, you're going to get 0 instead of 2 to the minus 2m as you should. So that's not a two universal family. Here's an example of a two universal family that we've seen before. Instead, I'm going to take fy of x, instead of the bit by bit parity, I'm going to take the inner product. So now that's a single bit in 0, 1. So we have only one bit of output, but you can check that this works. So this family of functions satisfies the condition of two universality. I recommend that you pause the video right now and check for yourself that this is correct, but otherwise you'll see it as part of the problem set. In any case, in the next example module, we're going to create a larger family of two universal hash functions. So now we have a notion of two universal hash function. Let's connect it to the notion of a strong seeded extractor by showing that if you have a family of two universal hash functions, then you can use this to construct a strong seeded extractor. So let's see the idea for the proof for the case where there is no side information. So purely classical setup. In the next modules, we'll use the same proof, but build upon it to treat the more general case where the side information is an arbitrary quantum state. So the setup for now is that we have the source, x, which is a n-bit string. It has min entropy at least k. And we apply this extractor, which chooses a seed y uniformly at random and produces the output z, which is determined by applying a function chosen using y from a family of two universal hash functions to x. And our goal is to show that the output of the extractor is uniformly distributed. In fact, more than this, we'd like to show that this is a strong extractor. So we want to show that the joint distribution of the output z and the seed y is uniform over m plus d. We're going to do this in two steps. In the first step, we're going to bound what's called the collision probability of x and y. The collision probability of a distribution in general is just the sum of the squares of the probabilities of that distribution. intuitively, the lower the collision probability, the closer to uniform the distribution is. And in the second step, we'll make that intuition formal by bounding the trace distance or the statistical distance, and since we have classical variables here, between the output z and y and a uniformly distributed pair of strings as a function of their collision probability. Let's start by bounding the collision probability. So we have to evaluate the collision probability of y and z. Now, by definition, this is equal to the sum over all possible values they can take of the probability that y is equal to y and z is equal to z squared, which I can split as the sum over all y and z of the probability that y is equal to y squared times the probability that z is equal to z conditioned on y equal to y squared. Now, if we spell this out, we get the sum over y and z. So the probability that y is equal to y is uniformly distributed, so that's just 2 to the minus 2d. And the second term I can write as the sum over x, possible values for x, of the probability that I sample x, times the indicator function that fy of x is equal to z. And all this is squared. So now we can expand this last expression. We'll get the sum over all y and z of 2 to the minus 2d times the sum over all x and x prime of the probability of x, the probability of x prime, these probabilities are taken under the distribution given by x, times the indicator that fy of x equals z and also fy of x prime. Alright, so here we have two cases. Either x is equal to x prime, in which case this will always be the case, or x is different from x prime, and then we can use the property of a two-universal family of hash functions, which is saying that in that case, the probability over y that this happens is equal to 2 to the minus 2m. So we get two terms here. When I sum over all y's, there's 2 to the d possible y's, so I'll get 2 to the minus d times. The first term is the term that corresponds to x equals to x prime. So this will be probability of x squared. So that's the collision probability of x. And what you can show is that because the min entropy is at least k, the collision probability can be bounded by at most 2 to the minus k. So here I'll get 2 to the minus k, and the second term corresponding to those x different from x prime, using the property of two universality, I can bound by 2 to the minus m. Once I've accounted for the summation over all possible z's here. So this is the final bound that we get for the collision probability. Now the second step is to leverage this bound the statistical distance. What we really want to estimate is the sum over y and z of the probability that y is equal to y, z is equal to z, minus what I would get under the uniform distribution, which is 2 to the minus d for y, and 2 to the minus m for z. Now here there's a step that I'm going to skip here, but what you can show using our application of the Cauchy-Schwarz inequality is that for any random variables, this is always going to be bounded by the square root of the number of possible values, so 2 to the d plus m divided by 2 times the square root of the collision probability, y, z, minus 2 to the minus d plus m. So 1 over the number of possible values, and it's the square root of this. Let me separate these two steps. Alright, so what I get if I use the bound from the first step of the proof is that 2 to the d plus m over 2, then the d plus m here cancels out with the d and the m here, and the only term I have left is minus d minus k. There's the square root, so we get 2 to the minus d minus k over 2. And this is equal to 2 to the, what's left is m minus k over 2. And that's your epsilon. It's the error parameter of the extractor. So what you see is that as long as the number of output bits m is much smaller than the min entropy of the source k, we get an epsilon which is exponentially small, meaning we have a very good correctness parameter. This means that this extractor built on two universal hashing is actually pretty good because k is the entropy of the source And this is saying that as long as we try to extract fewer bits than the number of unpredictable bits we had to start with, then the extractor has a low error parameter. So this is great, it's going to be very useful. Let's summarize it as a lemma. The lemma is called the leftover hash lemma. And it says that if we take a two-universal family of hash functions, h, that maps n bits to m bits, then the extractor that's defined from this two-universal family of hash functions is a strong-seeded extractor for source min entropy k and error parameter epsilon, as long as the min entropy is at least the number of bits that we're extracting plus a logarithmic dependence on the error parameter. So this extractor is actually a very good extractor. This dependence on the error is the thing that matters the most for us, and it's very good, logarithmic. Then the dependence on the output length is also very good. The only way in which the extractor is not so good is that the seed length that's required in order to construct these universal families of hash functions is typically a little bit long. Using more elaborate constructions, you can improve on this. But because for the application to privacy amplification, the seed length is not the most important parameter, we're going to put this aside, and in the next module, I'll show you how to construct a family of two universal hash functions.